Hey guys, Miss Hanley here. This video corresponds with assignment 3 in your trigonometry unit, unit 5. Excuse the typo up above. We're going to talk about arc length, speed, and also area of a sector in terms of all the circle information that we have been learning over the last couple of days. So the first thing that we want to talk about here is arc length. The formula for arc length is given up above. The arc length is represented by S, and S is equal to your radius times the angle, which is measured in radians. So we call this angle symbol theta. Theta is measured in radians. Note that if the radius is 1, then the arc length is the same as that angle. And let's look at the example below, and then we'll talk about how to find maybe just an angle given the arc length and a radius. So in the example below, a circle has a radius of 4 inches. Find the length of the arc intercepted, so that just means the portion of the circle that the angle is open up to. For example, if that's your circle and here's your central angle, the arc length that's being intercepted by the angle is this piece right here. Alright, so in our circle we actually have a central angle of 240 degrees, so let me sketch this here. So if we start in standard position, 180 would put us at would put us straight over, and so 240 would be about there. And we know the radius is 4. So we want to find the arc length according to this. And the key here is that theta is measured in radians. So if I know I have 240 degrees, I want to figure out what that is in radians. So use the conversion measures that we did last class. If you have 240 degrees and you want to convert to radians, you want to multiply by pi over 180. Zeros cancel. 24 and 18, well 6 goes into both of those. 6 goes into 24 4 times. 4 pi, and into 18 3 times. So our angle in radians is 4 pi over 3. To find our arc length, we need to take that radian measure, 4 pi over 3, and multiply it by the radius. So here we're going to get S is equal to 4 pi over 3 times 4, or 16 pi over 3. And that will be the length of our arc that is intercepted by the central angle of 240. Sorry about the screaming noises in the background. My fiance is currently watching The Sopranos, and I just asked him to turn it down. But anyway. So let's move on to the next slide here, and we're going to talk about how to find an angle if you're given an arc length, and a radius. So let's say I have my circle. Alright, and I have the center of the circle. We know that the radius here is maybe 7, and this arc length here is 9, let's say. And I want to find the radian measure in between those. Well, if you think back to when we first started learning about radians, our formula for theta is taking your arc length and dividing it by your radius. That's how we figured out what 1 radian was. 1 radian is when these two are equal, when your arc length is equal to your radius. Well, in our case, our arc length is different than our radius, but we can still use this formula to find the value. So in this case, theta of this circle would be equal to my arc length, which is 9, over my radius, which is 7. That's how many radians that angle would be, and that's determined by the relationship between the arc length and the radius. Okay, keeping that same idea going, let's talk about linear speeds and angular speeds. Consider a particle moving at a constant speed along a circular arc of a radius r. So whatever you have is moving at an arc, moving in an arc. Excuse me. If s is the length of the arc traveled in time t, so again s is that arc length, and then t is how long it's going to take, the linear speed of the particle is equal to the arc length divided by time. And linear speed is always measured in, it's given to you as distance over time. So it's how far it can travel in a certain amount of time, which is what we usually think of speed as. So in this case, let's try and break down this formula a little bit. S is our arc length, and we were just talking about S as theta times your radians. So this formula could really be rewritten as, sorry, not your radians, radius. Theta is in radians times your radius, all divided by time. So that will help us out in a little bit. The other thing is angular speed. All right. So this tells you how many rotations or how many degrees or how many radians your particular particle can cover in a certain amount of time. So it's how many rotations in a certain period of time we can have. So angular speed and linear speed, two different things. For angular speed, you just need the central angle divided by time. And you'll see this little symbol here, it's omega. Looks like a W almost. It's a Greek symbol. So let's try a couple examples. The second handbook clock is 10.2 centimeters, as shown in figure 4.16. We want to find the linear speed of the tip of this second hand as it passes around the clock face. So, if we want to find linear speed, the formula that we are going to need is the arc length over the time, and the arc length is theta times your radius over time. Well, let's think about this second hand and its rotations. Now, it doesn't tell us what type of an angle or what type of theta we should use. This clock is going to keep going continuously, right? So there's an infinite amount of rotations that will happen here. So we could pick any portion of a rotation and use that as our theta. So I'm going to think about this right here as, well, let's think about it one way, an easy amount of rotation, and I have to think about it in radians. So I would either want it to rotate 90 degrees, that would be pi over 2, but then I'm going to have a fraction inside of a fraction to deal with. So the nearest one that would be simple would be an angle of pi, right? If we go 180 degrees, we're going over here, and I'm going this way because this is the direction the clock will go, but we're just trying to figure out the angle that it's going at. So here we covered pi radians, so I have a linear speed of my theta is equal to pi. My radius is never going to change, that's 10.2. And the time that it's going to take to go from here, 15 seconds, over here to pi, which is at 45 seconds, would be 30 seconds. So I get pi times 10.2 over 30, and that would simplify to 1.068, and this is in centimeters, so it's centimeters per second. Now again, we didn't have to choose pi. We could have chosen it to go all the way around, which, oops, that's not what I meant to do, which would put us at 2 pi rotations. And if you think about your clock, how long is it going to take to go from 15 seconds back around to 15 seconds? Well, it takes 1 minute, right? So the other way we could write our linear speed is by saying, well, it went 2 pi radians. The radius is still 10.2, and this time it took 60 seconds, or it took 1 minute, which would give us 20.4 pi centimeters per minute. Or if you didn't do it as minutes and you wanted to stick with seconds, it would be over 60 seconds. And this divided by 60 is going to give you that same 1.068 centimeters per second. So either way you would like to think about it, doesn't matter how many rotations you decide on, you just have to make sure that your time is corresponding to that. Okay, so for the next one, we're going to look at a situation with a Ferris wheel. It has a 50-foot radius, and it makes 1.5 revolutions per minute. We want to find both angular speed and linear speed of this Ferris wheel. So let's start with our angular speed, which we used omega to represent that. Mine looks like a W, but you can do better than me. And that is just your central angle, so theta, divided by time. So if we want to find out our central angle, we have to think about how far this Ferris wheel is going to move. And again, think about starting in standard position, how far it's going to move in 1.5 revolutions. So if I start here and it makes 1 full revolution, how many radians would that be? Well, it would be 2 pi because we went all the way around. And then it has to go another half a revolution, so we'd be adding on another pi. So altogether this has gone 2 pi, and then 3 pi would be my central angle there. So our theta is 3 pi. And the time that it's going to take to do that is 1 minute, because it says 1.5 revolutions per minute. So 3 pi over 1 gives me 3 pi, and that is how many rotations we're going to have in 1 minute. So, or how many degrees you're going to go in 1 minute. So we say radians per minute there. Alright, and then our linear speed, v, is our arc length divided by the time. So arc length is theta times your radius over time. Theta we just determined was 3 pi if we do 1.5 revolutions. The radius of this Ferris wheel is 50 feet. And the time that it takes to do that, again, is 1 minute. So this would give me 150 pi, and that's going to be feet per minute. That's how far we traveled, how many feet we traveled in 1 minute. And you could certainly do 150 times pi and find an actual value, but leaving pi in your answer keeps it exact. So that's a good way to look at it. Alright, and then lastly for this piece is area of a sector. So we were looking at finding just the arc length, just this distance around the edge here. But now we want to think about the area. What's the amount of space that that would take up? So for the area of a sector, you have area is equal to 1/2 times your radius squared times theta. And again, theta is in radians. So let's look at this example here. So again, we have 1/2 radius squared theta. Okay, so we have a sprinkler on a golf course fairway. It's set to spray water over a distance of 70 feet, and it rotates through an angle of 120 degrees. We want to find the area of the fairway that's watered by the sprinkler. So we want to figure out how much grass is being covered by the sprinkler. So first of all, they gave us an angle in degrees, and we have to convert to radians. So my theta is going to be 120 times pi over 180. Again, the zeros cancel. 12 and 18, 6 goes into both of those. So this would give me 2 pi over 3. and then I can substitute into my formula. So I have 1/2. My radius squared would be 70 squared, and then times theta, which is 2 pi over 3. And we could continue, and we're going to end up with 5,131.27 feet squared there. This time I actually multiplied in the pi. You could certainly leave your answer with pi still in it, and it would be more exact. But this just gives us a little bit of an idea of actually how much area this water is going to cover.